Okay, so in the last lecture, we started discussing the ripple carry error topology again. We discussed how the same topology could be used as a subtractor as well. And then we discussed how you can incorporate a control signal to selectively use the same hardware for addition or subtraction. We then discussed how carry is a major bottleneck because that leads to significant delay because of the chain structure. And we also looked at a circuit structure and discussed how a carry signal drives many capacitors, and that's why it's the slowest signal in the circuit. And that's why we have to do something about it. We have to find a way to make this carry propagation faster. And in that regard, we discussed a new concept called carry look ahead, right? It's a new kind of adder architecture that uses a prediction of the carry without letting it ripple through the chain. All right. So uh, basically, as I told you in the last class, that every time we need to come up with a new idea for adder design, we always go back to the truth table and try to find new ways to describe the pattern. And this is just one way to categorize the rows of the truth table into different signals like delete signal, propagate signal, and generate signal. And we came up with three expressions that discuss these three type of signals: delete, propagate, and generate. All right. And for this particular adder topology that we'll be covering in this course, we only need propagate and generate. We don't need the delete signal. That's a different kind of adder that we'll not cover for 255. Okay, so if you use that intermediate signals, propagate as A XOR B and generate as AB, then you could represent the carry and sum function as something like this. Something like this. Sum basically deals with propagate and input carry, and carry output deals with generate and input carry. What was the big deal? The big deal was here. So basically, you could express the carry output of any stage using the very first carry. That is a very powerful situation. Let me show you again, once again. So imagine you have, I mean, we discussed this in the last class, but that was the last slide we discussed. So that's where we begin again. So A0 and B0 is the first bit that you're dealing with. And you have a carry in, and you have sum and carry out. Okay, so let's consider that this is basically C0, or 1 second, or we could name it as C0 and the other one as C1, however you want to do it. Nowadays, this interface, PowerPoint interfaces started causing some issues, but anyways, so C1 and C0, let's do it. So do you guys remember? I hope by now you should try to memorize this almost, right? Sum was what? Propagate XOR C in. What is C in? This is C0 for now. Okay, but sum was never the issue. The issue was carry. So carry out was G plus PC. What is the generate signal? It is AB. What is the propagate signal? A XOR B. Okay, so can I express C1, which is the output for this stage, as generate for 0th stage, propagate for 0th stage, and carry for 0th stage? Can I do that, folks? Okay. All right. Now imagine you are driving another adder output, which is C2, like carry output, with the adder that we currently have. So how will that look like? Let me just do it on the side. C2 will be, if you use the same formula here, G1 plus P1 C1. Can I write that? Like one less, right, in terms of indexing. So in that case, can I replace C1 with what we had here before? So I'm going to do G1 plus P1, G0 plus P0, C0. which is G1 plus P1 G0 plus P1 P0 C0. So C2, just take a look at how you're expressing C2. You're expressing it with respect to the very first carry that you provide. It's no longer dependent. Notice, this is the big deal. It is no longer dependent on the carry of its immediate previous stage. It is directly linked to the very first carry, which you can control. Are you all okay with it so far, folks? So, and you could keep doing it for C3 and C4, and that's exactly what you get in this slide. So any carry at any stage, for example, I plus 1th stage is linked back to the very first carry. I plus 2th stage, again, link back to the very first carry, and so on. So you could link all the carry outputs down to the very first carry that you provided. What is the big deal there? Because the very first carry doesn't have to trickle through or ripple through the chain. It basically is an input, right? So you don't have to wait for the carry to ripple through the chain to calculate the next carry. You could pre-calculate all the carries. The moment you have this input, CI, you could pre-calculate all the carries. And remember, carry was the bottleneck, right? You were waiting for the carry. Are you guys all with me so far? Okay. So, and I told you that that is the bottleneck. So if you could somehow find a way to bypass that stage, and that means you don't have to wait for the carry to be generated. And this is what an architecture like this looks like. Please pay attention. This stuff could be boring if you don't understand this properly. Otherwise, it will be like, okay, boxes here and there and some arrows, right? So let's try to make sense of it. Okay, take a look at this structure. This is full adder, full adder, full adder, full adder. So basically, it's kind of like a ripple carry adder. One adder driving the other, because every adder deals with one bit, right? So here you are dealing with how many bits? Can anybody tell me? 4 bits. 4 adder blocks, 1, 2, 3, 4. So I'm dealing with 4 bits at a time here. What is the difference? Can you take a look at this architecture and tell me, in your opinion, what changed between this and a ripple carry adder that you saw before? What is the difference? Ignore this block for now. Just look at the chain up top. Just look at the chain on the top. What changed in the chain? Yes. Yes, thank you. Did you see that you are not really providing any direct carry output in between the neighboring stages anymore, right? Which was the case for ripple carry adder. The carry was rippling through the chain. But now we broke the chain. Notice, this stage is not waiting on the previous stage to calculate its carry. Similarly, this stage, which is the third one, is not relying on the second stage. Fourth stage is not relying on the third stage. So you're no longer waiting. Okay. And how do you pre-calculate the carry? Here is how. Notice, there is a carry calculation block. This is 4-bit carry look ahead circuit. And I'll show you what that circuit is. But for the time being, just bear with me. So somehow you create a block that generates or calculates all the carries for you. Carry for 0, 1, 2, 3. Right? All the carry positions for you, pre-calculates. And then notice, this block basically feeds the carry to wherever they are needed. So you needed to have C1 being fed to the second stage. Sure, directly feed C1 from the block. Carry look ahead adder block. Directly feed C2, directly feed C3. If you can find a way to calculate them. Are you still with me? Okay, so that is the difference. Just to break the chain, just to avoid the ripple effect, we have to create a new block that pre-calculates the carry look ahead, basically. Now, based on your understanding so far of the course, let's see how much you understood, honestly. Or are you just rushing for your CGPA? That's the difference, okay? Can anybody tell me how I can incorporate this block? And I'll give you a hint. The answer lies here. Can anybody tell me? Just treat carries as outputs. So this is your first output. Okay, imagine, let's put some number here. Let's put I equals 0. Let's put I equals 0. Okay, can we do that? Say if I equals 0, what will be this one? This equation will be C1 equals G0 plus P0 C0. Is that okay? Okay. Now, what will be the next one? Since I equals 0, this will be C2 equals G1 plus P1 G1 plus P1 P0 C0. Does that make sense, folks? Okay, hold on. And I can keep doing it for the rest of them, for all 4 of them. But can you see that this is nothing but a logical equation? Can you express that using AND gate, OR gate, blah, blah, blah? Can you do it? You treat G0, P0, and C0 as what? G0, P0, C0 as what? Inputs, right? Okay. And notice all of this carry will have C0 as an input. And C0, you don't have to wait on C0. It's the first carry. You just feed it in. How about G0 and P0? Notice the only thing that was slow, by the way, you were waiting on that was carry. But remember what is G? Generate was A XOR B. And when do you think A and B are available? At the start of the operation. You don't have to wait on A and B. You begin with A and B, basically. You already know A and B. So you directly calculate G0. So when you try to get G0, you do A0 XOR B0. What is 0? 0th bit. When you try to get G1, that's the first bit. G2, that's the second bit. But you can do an bitwise XOR. Yes. Oh, I'm sorry. I meant to say propagate. Sorry, my bad. Thank you for catching that. All right. I misspoke, folks. Just, don't get confused. So propagate was A XOR B, right? Yes, remember? And generate was AB. So irrespective of that, thank you. Irrespective of that, what I'm trying to say is, do you need to wait on propagate and generate to be calculated at all? Because A and B signals, or numbers basically, they're available right away at the very beginning of the operation. And when I try to calculate propagate 0, I do A0 XOR B0. When I try to calculate P1, I do A1 B1. And I hope you remember A0, A1, A2, A3 is basically the number. It is available to you. Same applies to B. It is available right away. So there is absolutely 0 wait. So you can calculate. Now, take a look at any random equation, this one. You don't have to wait on generate. It's available right away. Propagate available, generate available, propagate available, generate. All of these signals are readily available. And the only thing that you could have a concern about was the carry. And notice you have somehow linked it back to the very first carry, which is also readily available. So all of the signals are readily available. So you don't have to wait for this carry to be generated. So at the very beginning of the add operation, even before you calculate the sum, by the way, you basically calculate all the carries using the carry look ahead circuit. Does that make sense, folks? It is not important to memorize this structure, but it is important to understand how it is different. And again, if you don't understand the problem, you will never be able to solve the problem because you don't know what the problem is, right? And also you have to identify the most critical issue to solve it. Notice they haven't changed anything about the sum generation because sum was never an issue. The only issue was carry because it was being propagated. So they completely got rid of the propagation part and pre-calculated all the carry. And I think I mentioned that in one of the previous classes. There is no free lunch in engineering. Okay, you gain something, you lose something else. Can anybody tell me what you are losing by using this approach? Yes. Thank you. Yes. I mean, I was just waiting for you to ask this question. Hold on a second. Just to pre-calculate this carry, just look at the complexity of the function, right? Don't you think? How many AND gate or gate do you need to incorporate that? This is easily 1, 2, 3, 4, 5. 5 input AND gate, and then you have a bunch of OR gates. And this is just 4. Fourth carry. Imagine you are trying to add a 32-bit number with another 32-bit number. Can you even imagine the complexity of the logic, right? This is insane. So what do? Engineering is basically all about optimization. Like I said, yes, you have a feature that you get, you pre-calculate carry, but how much can you take? Just look at when you do fourth carry calculation, you have such a complicated situation. So how about we never go beyond 4? Like we just always have blocks of 4, because if I go to 5, it will be like tremendous. 6, unimaginable. 32, I mean, it will make absolutely no sense at all. You know why? Can anybody tell me why? These are, I mean, I don't know how many of you have given interviews yet. They ask you questions that are really fundamental and they want to see whether you understand. They don't want to see whether you memorize or remember, because you'll never be working with these adders in actual industry. They have much better design. You know, something that you're being taught in classroom, that means it no longer matters to the industry. Right? Because they have more cutting edge designs, of course. Otherwise, they will not be publicizing it to everybody for free. Am I making sense, folks? Then how will they have a business? They need to have exclusivity. They will have trade secret. They will not publicize this to everybody. But if you understand these basics, only then they will be able to share their advanced design with you, because you have the capability to understand the basis. Okay. So, okay, let me ask you this question. That is, imagine that the only problem that I'm trying to solve by using this carry look ahead approach is the delay. Okay, that's the delay. All right, so the delay between, like, how long it takes to propagate the carry from here to there to there. Do you have any concern about going up in the chain as the complexity grows? Do you think the delay will remain the same? Did I tell you that the more gates, more inputs you have, the more capacitance you get eventually? So at some point, if you go to like 32-bit carry, the time that will take to pre-calculate, yes, if you have everything ready, you have all the recipes, like you have all the ingredients to cook something, but it simply takes more time to bake. Something takes 5 minutes to bake, something takes an hour. So this will probably take an hour to bake. Yes. It's always going to calculate all the way to the end every single time. Yes, exactly. So in principle, I could have a 32-bit adder and calculate all 32 carry output at the very beginning. I don't have to wait for the chain. That's the hypothetical scenario. But should I do that? In principle, it looks like, yeah, sure, why not? But when you think about the practicality, because this is just maybe fourth carry or third to fourth carry, right? It is already so complicated. When you get to fifth, sixth, seventh carry, you will not be able to write the equation in a slide, for example. It's so big. So just imagine how the circuit will look like and how much capacitance you'll be dealing with. So then, yes, you have all the inputs available right away. You don't have to propagate. But then just to calculate the carry, it will take you more time than what it would have taken to just propagate the carry. Does that make sense? And nobody just makes up these numbers. They do simulation, by the way. Nobody just goes and designs something and then, oh, it doesn't work. They simulate. So you will simulate at some point, and you will actually have a hardware design and see how much can we handle. Can we do 5 bits at a time, 4 bits at a time, 6 bit, 8 bit? How many bits will be the most optimum situation? That will still be faster than ripple carry, but you see my point, I hope, right? So based on that argument, notice this is a 4-bit block where you have a carry look ahead circuit. Notice, folks, and you generate the fourth carry, C4. Okay, now when you try to incorporate, say, 16-bit add, how do you do it? This is the architecture that people figured out. It's a mix of ripple carry and carry look ahead. So you don't look ahead all the carries. You look ahead blocks of carries, like 4, 4, 4, and then you ripple that one. Instead of letting it ripple through 16, you let it ripple between blocks. Am I speaking to myself? Okay, all right. So allow me to explain that. I know blocks are never fun if you don't understand them. So please pay attention. I hope you will understand. Yeah. Yes. So imagine, so this is essentially 16-bit. I hope you can see that it's up to A15, starts with A0. So 16 bits, right? We're trying to add 16 bits. So instead of, we could have just had a giant carry look ahead block that predicts all 16 carries, but we don't do that simply because it will be like, outrageously complicated to implement that in hardware. Of course, it will take more area, as you said, because everything takes area. But more importantly, it will also take more time. So it will defeat the very first thing that you're trying to solve. You're trying to make it faster, but you'll eventually make it even slower. So here is what we do. So you have the 4-bit block that we just talked about. You deal with 4-bit at a time, A0 to 3, B0 to 3. Remember, we often just bundle together multiple bits to show them. So there are 4 full adders actually within this block, but it is being represented as a bus. Okay. So once you figure out the carry output, which is, just remember the last slide, we calculated the last carry from this one, and we could provide the carry 4 to the next block as the input carry. Notice there was an input carry here. So you just use it as a Lego block, and you use this final carry as the input carry for the next block. So every block has like 4 full adders. Let me zoom into this again. So this is your input, this is your output, and just copy this block over and over again. And now, aren't you rippling the carry almost? You see that? So you ripple the first one and the 4th one and the 8th and the 12th and so on. But you don't ripple everything. So that's how you speed up, but also ripple a little bit. So you make a compromise. Does that make sense, folks? Okay, and I highly recommend, it will only make full sense once you go back and read about it here, and then try to explain the block to yourself. And trust me, if you try to explain something to someone else, like your friend, I highly encourage discussion among your friends, okay? When you try to explain something to someone, you only then realize whether or not you really understand it. Does that make sense? Don't feel like, oh, okay, I got it. Because you probably haven't, right? Just make sure that you try to, even if you're trying to explain it to yourself, try to speak up, basically. Okay, let me try to explain this. Here is how things are working. And nobody needs to know. It's just you in front of a mirror, or not, maybe nothing, just yourself, right? And see whether you can really explain it to yourself. And not just for this slide, of course, I mean in general. If you don't understand something or you cannot explain it to yourself, rethink, take help while you are here during the semester. You can easily find me. Of course, you can find me after as well. But, isn't it easier to find me during my office hours now, or while the semester is still going? That way, benefit the most. Okay. This is just another example in a lower granularity. Like, we are getting deeper into the details now. I hope it will help you appreciate the area aspect, as you pointed out, right? We just showed it as a block. Okay, just a block, a rectangle, but it's never really a block, is it? It is a complex network of circuits. And I hope we can now count how many AND gates and OR gates we'll need. As we just said, for this particular term, it has 1, 2, 3, 4, 5 inputs. So it needs a 5-input AND gate, and then 4-input AND gate, and then 3-input AND gate, 2-input AND gate, and then 1, 2, 3, 4, 5-input OR gate. If you just do 2-stage implementation, then if you break it down into multiple stages, it will take even more, maybe, right? So considering that, this is a more realistic scenario as to how it looks like. And this is dealing with 4 bits. Notice A0, A1, A2, A3. Okay. This is the first carry that you provide, C in. Notice that. This is just another view of this slide. But instead of showing you 16, which will be like an overkill, it will not fit in the slide. We are looking at a 4-bit scenario. Imagine in a 4-bit scenario, you have 2-bit carry look ahead blocks. Am I making any sense? Okay, in a 16-bit scenario, we have 4 bits look ahead blocks, right? In the previous slide. Here, we are just reducing the number space a little bit just to make it more manageable to show. Imagine your total number is 4-bit and your carry look ahead is just 2-bit at a time. Can I not extrapolate it to 4-bit? or can I do that, folks? I mean, I get nervous when you're so silent. Okay, let me repeat that. What I mean by that is here, your numbers were 16-bit, and that's more realistic, honestly. You have 16-bit numbers, and every carry look ahead block was how many bits, folks? 4. Now, if I try to draw that using this level of granularity, okay, this will be really complicated and difficult to track. So we decided to reduce the number a little bit. Instead of 16-bit digit, we're dealing with 4-bit digits to make it manageable. And instead of 2-bit carry look ahead, sorry, instead of 4-bit carry look ahead blocks, we're looking at how many bits? 2 bits, okay? But can you not extrapolate it to 4 or even more bits? You can if you use, let's see whether you can get the point at least. Okay, the point is you have A0 and B0. You calculate, let me zoom into this one. Please pay attention to this. Can anybody tell me what this logic gate is doing? Try to understand looking at the circuit. This is A0 and B0. This is an AND gate or OR gate? AND gate. What do you get here? A0, B0. Do you guys remember that generate signal was what? AB. So this is essentially your generate 0. G0, okay? What is this gate, folks? XOR gate, thank you. Yes, notice this one. So this is essentially giving you A0 XOR B0, which is your propagate signal, P0, okay? All right, and what is this one, folks? This carry input is being fed here. I hope you are following as I draw, because, okay, let me change the color. Which one? Maybe red. So carry in is coming here, going as one of the input to this AND gate, and the other input is what? Propagate signal, right? P0. Can anybody help me understand what this guy is doing? What this is an AND gate. This is giving you P0 C in, don't you think? And then finally, there is an OR gate here, which is adding this G0 with P0 C in and giving you G0 plus P0 C in, which is your carry output. If you don't remember, let me go back to this slide again and show you. Remember, carry output was G plus PC, right? So you are getting G plus PC from this final gate. So you need all this hardware to be in place to calculate G0, P0. So don't you think you need something similar for G1, P1, and so on, right? Okay, and by the way, you notice, and by the way, you calculate the sum. How do you calculate sum, folks? Do you remember the expression for the sum? Propagate, XOR, carry in. That was the expression. Can anybody help me understand how that is being done here? Notice there is an XOR gate sitting here. Sum 0. It is taking, let me erase everything. Let me just make sure. This is the XOR gate that I'm talking about. You are getting carry in right away. And what was this signal again, folks? This was the propagate signal, remember? As I just told you, A0 XOR B0 is basically P0, which is propagate. So what is this sum? P0 XOR C in. Wasn't that the expression for the sum? So that's how you add. You get the sum out of these XOR gates and you get the carry. Okay? And one more thing, folks, you might remember previous slide. We relate all the carry output back to the very first carry. So the only thing that you need to provide to all this hardware is the very first carry. As long as you go this carry look ahead route. Okay, so let me show you here. Notice this carry, the very first carry input is being fed here as well as the next stage. You see that? It is being fed to 2. Okay, quick question. If I try to incorporate 4-bit look ahead logic, so this is a 2-bit look ahead logic. We just look ahead 2 carry at a time. not more than that. If I do 4-bit look ahead, how many branches will this carry in deal with? Help me understand. How many? So every carry that you calculate, you need to provide this carry input, right? So let's go back here. These equations will help you understand. Okay, let's see. This is your first carry, C1. This is your second carry, C2, C3, C4. So if you try to calculate these 4 carries, how many times will you need CI? 4 times, right? So you need to branch it out 4 times. Instead of 2, you need 2 more, maybe somewhere else. Does that make sense? But then you only provide C input to everybody. And what do you calculate eventually? You calculate C4, which is the final output for the carry of that particular block. This is very tricky, I know, like to keep track of. And when I say see your sad faces, I can relate myself to it. Trust me, it's not unmanageable. I know it can be a little bit boring, especially because it's full of blocks and you have never seen that before, I guess. So the first time you see this type of stuff, it's always, not fun. So it's okay. I'm with you. Don't feel like you're lost. Okay. You'll be okay. Even if you don't get it in like today's class, you will get it. Uh, what I recommend, my recipe would be try to do it, try to explain it yourself. And that's why I provide the recording as well, in case that helps. If it doesn't, it's fine. You don't have to listen to the recording. You can listen to me again. Maybe, but I request that please seriously try to explain it to yourself by yourself at home. And then you can come and talk to me again in case it doesn't, appear to be clear. Okay, so concluding remark is you provide the carry output from one block to the next block as if that is the new carry in. So this is your new carry in for the next block. So this bluish zone is the CLA, carry look ahead logic. And then this is again carry look ahead logic. And there will be carry look ahead logics in every stage. So you could use this 2-bit look ahead logic and use it as a Lego block. Or you could do 4-bit look ahead logic, use it as a Lego block. I've even seen 8-bit look ahead logic. It makes sense in some cases, for example, and go through the chain that way. All right. So that is carry look ahead adder. And by the way, this is the last slide. There are many other options. This is just one kind of adder that you have seen beyond the ripple carry adder. And these are some names for you to consider, but I don't want you to, or need you to study this at this point. For example, I covers all of these 4 other types in 433. This is just a flavor that you're getting as to like what is out there. Ripple carry adder is the very basic, plain vanilla kind of thing, but it never really works in practice. Okay. All right. So with that, we are done with this lecture. I'm happy to move over to the new lecture. But please, I keep repeating myself. Please make sure not to wait for the very last moment before the final exam when you start studying, because everything is linked. If you don't get it properly, the next stage will not make sense. And the way this particular course is designed is they build up on each other. And I keep referring back to, remember we talked about XYZ, right? So if you don't understand that XYZ, the next stages will also be meaningless at some point, and you'll easily be frustrated and like, oh, okay, this is not my field. I don't really like it. So that's how things work typically. So don't wait until the last moment. Please make sure that you review everything. Okay, so in the next lecture, we will discuss a different flavor of logic circuit. It's called sequential logic. Okay. So far, the type of logic that we have covered, it's called combinational logic because of this reason. Let me show you. Because just look at this block. Your output of this type of combinational logic circuits were only functions of the combination of inputs. So you have a few inputs, 3 input, 4 input, 5 input, whatever the number could be. And based on the combination, is it 0, 0, 0, 0, 1, 0, 0, 1, 1, whatever, right? Based on the input combination, you decide on the output situation. Is it going to be 1 or 0? Okay, so that's combinational circuit. There is no history in this circuit. There is no feedback in this circuit. And the outputs are only function of input. This is the expression that you should keep in mind. Output is just directly function of input. However, there is a different flavor of logic, which is like this, which not only considers the combination of inputs, but also the history of the circuit. How was my output before? How was my output like 10 nanosecond ago? Something like that. So based on the history of the output, it can choose different outputs actually. So basically your output is fed back as another input. So these type of circuits, what we call, they are history dependent essentially. They are function of inputs, of course, but also previous inputs. Am I making sense? It is not just a function of the current and existing input set. It is also a function of the history, which is basically what was the previous set of combination applied to me? Okay, now I have 1 on 1, but in the last cycle I had 0 0 1. So based on what it had in the last cycle, its output can change. So that is a sequential logic. As the name says, there is a sequence involved. Okay, you have to maintain certain sequence to change the output into certain way. So you have to be mindful of the sequence that you use. So it's more complicated, obviously. And notice, in the heart of a sequential logic will be combinational logic, don't you think? So whatever you have learned so far, combinational logic, will directly be applicable. Nothing will be taken away from it, except for the fact that there will be some feedback loop from the output to the input. That's it. So what you have learned is building towards sequential logic. That's why it's showing up right now. Okay. I will jump in and start showing you some direct example, and then we'll take a step back later on. Okay. So the first example of a sequential circuit is a latch, and I'll show you the concept of the latch first, and then we'll see the circuits and whatnot. This is just a block diagram of a latch. What it does is, let me explain. And please pay attention while I explain, because I'll be marking on top of the figures, and after it will be messy. So this is a block diagram. D stands for data, Q stands for output, okay? And G, or whatever this input is, it could be a clock signal. So clock is just like a pulse, okay? So it goes from 0 to VDD, or high value, whatever that voltage value is, inactive to active, inactive to active. So it's like a pulse signal, okay? And this is your input, this is your output. Your input is the data signal. Your input is fed to the output, driven by the clock. And let me show you how. There could be two types of latches, positive latch and negative latch. If you understand one, the other one will be like plain vanilla. The positive latch lets the input go to the output when the clock is high or activated. You can only imagine what the negative clock will do. It lets the input go to the output when the clock is 0. Exactly the opposite. If you must have seen that there is a approach in engineering to design complementary variants of different circuits, right? I hope that makes sense. Like some circuit and its mirror image. Okay, all right, clock, when the clock is high, input goes to output. But what if I want to do the opposite? Sure, let me give you another flavor of latch. That's a negative latch. It will let input go to the output when the clock is 0, in case you need it. Okay, so just two flavors. If you understand one, the other one will be like exactly opposite, like mirror image. Okay, so now let's see how that's going on here. This is your clock signal. Inactive, active, inactive, active. Okay, super simple pulse wave. Now this is your input. Why does it look so complicated? Because this is basically the norm in computer hardware books. They try to design or draw the input this way. What they mean is, let me show you. Just follow one of the lines. Input could go from high to low and back to high and low and back to high and low. They show that the input could keep changing. That's all. Am I making sense? It doesn't have to be like a scissor, as if like, okay, it doesn't really need to be like this. It could be like, okay, high to low and then stay the same. But they want to show that it's constantly changing. That's what they want to illustrate. That's why it's so zigzag. And by the way, what is the other line doing? They want to show without any loss of generality. If they only showed this one going from high to low, there could be a question, hey, why would it go from high to low? Why can't it go from low to high? They said, okay, sure. You could start with this, starting from low and going to high and then blah, blah, blah. The exact opposite pattern. It doesn't matter. That's what they're trying to, convey. That it doesn't matter how the input is changing. Let's assume that it is changing. Okay, that's why gets used to this type of pattern that you often see in textbooks, which used to freak me out when I was a student. Like, oh wow, I've never seen this type of an input before. Wow, it must be something so complicated. Okay. All right, are we all good? Comfortable with it so far? Okay, so this is an input essentially, which is changing. Whenever you see this scissor-like structure, it represents that changing. Whenever it's stable, of course, it's stable. It's not changing. Stable, changing. Stable, changing. Simple. Okay. And I'll explain the output, but whenever you see output doing this type of scissor-like behavior, you understand that the output is changing. And when it is stable, well, it is stable. Any confusion so far about this? Okay, let me explain when the output behaves the way it behaves. Okay. All right, notice when the clock is 0, and we assume, by the way, we assume without any loss of generality that our output was 0 to begin with here. Okay, notice clock is 0. Let's assume for the time being that our output was 0 to begin with. Notice the input is changing, but output is not doing anything. It's as if it doesn't even see the input. Are you all good? Okay. And then all of a sudden, when the clock becomes 1, clock becomes activated, notice what happens. Output starts mirroring the input. So the input gets connected to the output. Okay. So when your clock is activated, your input and output are linked now. And then again, once the clock goes back to 0, notice your output stops responding. Okay. And there is more to it. So I'm not done yet, but does this make sense so far? Whenever the clock is activated, your input is connected to the output. Okay, now let's take a little bit deeper look at this. First question, what if my output was not 0? Sure, if your output is 1, it's exactly the same, doesn't matter. That's why they have this crisscross structure. No matter where you start, it's going to be the same. If your output was 1, it will remain 1 until your clock is activated. Then it will start following the input. Whatever the input does, it will do. Exactly. Yes. It's a great question. I will answer that. Okay. It's a great question. Why do we call it a clock? And I will answer it a little bit later in the lecture. But please keep this question in mind. All right. There is a reason for that name. Okay. Any other questions? Okay. All right. Notice. So one more thing. Notice there is a vertical line being drawn from the clock edge to this point. And can you notice one thing here? There is a delay between the input and the output. I don't know if you have noticed that, but your output will not be able to completely follow the input right away. Okay, so this particular diagram doesn't illustrate that well, but we will see diagram coming in and you will see there will be a lag after which the output starts following the input. Okay, it is not illustrated here in this particular diagram, but keep that in mind. Okay, so now let me wait for a second and see whether you are all okay with this particular explanation. So this is a circuit which uses a signal called a clock, which basically keeps pulsating. Okay. And you could basically control the time period and timing. And maybe I can answer it right now. Basically, it has to do with the timing. What it does is it helps you synchronize the circuit. Okay. Now, what do we use a clock for? To synchronize things, for example, right? Okay. So you and your friend, you must see that in movies when they're trying to do something in a mission, they all have clocks. I don't know if you've seen this type of thriller movies. There is a mission, I don't know, and they all have clocks and they try to synchronize. Have you seen Fast and Furious? Like they have clocks and they make sure that they do everything in specific time. Okay, 5 plus 10. Let's do exactly that. So that's how you synchronize, honestly. You use the clock to synchronize. If I don't see my friend doing something in a different part, I know that at 11:30, I should do this and my friend will do something else. So that's how we can synchronize our work, even though we are not seeing each other. You see my point here? So, okay, we create a set of plan that I'll start the car at 11:30. I'll drive to the school at 11:45 and blah, blah, blah. And my friend will do exactly that at the given time. So we can synchronize our work even without seeing each other. Similarly, in a circuit, in a huge chip, when different components are all in different location, how can you synchronize their work? You can use a signal like this, clock signal. Notice, please pay attention because I was anyways going to cover it. It's not just for the question, okay? So it should also interest everybody. Notice, you can make your circuit respond only when your clock is activated. And you control when your clock is activated, right? Don't you think? So you can control its time period, it can control its duty cycle. And whenever this clock is activated, if you use the same clock signal in another circuit, they will both be simultaneously activated. And then they will be synchronized. Inputs and outputs will be synchronized. So we synchronize different components of the chip using this signal. So it makes sense to name it as a clock because that's what we use to synchronize our work. Am I making sense here, folks? Okay. Another example, I think this could be a better example, and I'm learning by doing things. Imagine, have any of you taken, I'm sure, SAT exam? GRE, you haven't taken GRE because you're not graduate students, but when I was applying for grad school, I had to take GRE exam. Okay, it's an international exam, for example. It can take place simultaneously, even if you're geographically in different location. It will all take place at a given time simultaneously. Okay, so how do you synchronize that? How do you know that, okay, someone from California and someone from New York is taking the exam at the same time? What do you use? A clock. Right, basically this could be a better example rather than going to school and whatever, but I'll keep that example in mind. So clock signals can be used to synchronize our work, and that's exactly what is used to synchronize the circuits. Yes. Such a big delay that a clock can actually make them. Absolutely, absolutely. I'm so happy that you asked that question. I was expecting that, but I mean, because given the time, I didn't want to get into that tangent. What if the clocks are not perfectly aligned, right? What if there is a delay between when I say that, hey, you take the same clock and put it to something else and they're synchronized. What if there is a delay? There is a gap between. This is called clock skew. This is known problem, and we handled. I'm so tempted to get into the detail of it. Maybe since you asked, I'll add an extra slide and I will show you next cycle. Designing clock and routing clock is a very big deal in this industry, semiconductor industry. Clock tree routing is a basic design approach. So first, people design the clock route. They balance the clock. There are different ways and algorithms to design the clock. And then they design the logic around the clock. Okay, it is so critical to make sure the delays are balanced. Okay, it's not an easy thing to do. That's why it's so tough to, speed up microelectronics. Anyways, we are right on time. I'll stop here, and I know I haven't covered the entirety, but I'll review it in the next class. No worries. Take care.